Back in 2018, Google dropped a model that totally changed the game for artificial intelligence. It was called BERT, and it was a massive leap forward in how machines could actually understand the way we humans talk. So, let's dive in and unpack the story of how AI finally learned to read between the lines.
Okay, so this is the fundamental problem, right? For years, AI could process words, sure, but it really struggled with what those words meant in a sentence. Think about the word bank. It means something completely different in riverbank than it does in money in the bank. So how in the world do you teach a machine that difference? Well, that was the exact challenge that BERT was designed to solve.
And here's the genius of how it did it. Now, BERT stands for Bidirectional Encoder Representations from Transformers. I know, that's a mouthful, but the key word you need to remember is bidirectional. You see, older models would read text in just one direction, left to right, like we do. BERT threw that out the window. It reads the entire sentence all at once. This means it understands a word by looking at everything around it, the words that come before it and the words that come after it. And that, right there, was the breakthrough.
But how did it learn to do something so amazing? Well, the real magic, the secret sauce, wasn't just in its design, but in its super unique two-part training process. This is what really gave it such a deep and powerful grasp of language.
So the training was split into two key jobs. On one hand, you have the Masked Language Model, or MLM, which is all about guessing missing words. And on the other, you have Next Sentence Prediction, or NSP, which teaches the model how sentences actually relate to one another. By getting really good at both of these things at the same time, BERT developed this incredible intuition for language.
Let's dig into that first task a bit more. The easiest way to think about the masked language model is like a giant game of fill-in-the-blanks. You give the AI a sentence, but you hide or mask one of the words, and its only job is to figure out what that hidden word is based on everything else it can see. And what's so clever about this is that it forces the model to actually learn. To make a good guess about that masked word, it can't just memorize a dictionary. No, it has to learn grammar. It has to learn which words tend to go together, and it has to pick up on the subtle relationships between ideas, all from the context of the sentence.
All right, now for that second task, Next Sentence Prediction. Here's how it works. The model gets two sentences, and it has to decide if sentence B logically follows sentence A. So in this case, the man went to the store, followed by, he bought a gallon of milk? Yeah, that makes perfect sense. The model would learn to flag this pair as is next true. But then you give it a pair like this. The man went to the store, and penguins are flightless birds. This is where the model learns what doesn't make sense. These two sentences have absolutely nothing to do with each other. By training on millions of these totally random pairings, the model learns to predict is next false. And in doing so, it starts to understand things like conversation flow and staying on topic. BERT's success was absolutely huge. But of course, the story didn't stop there. Almost immediately, researchers started building on what made it great. And that led us to the first major evolution, a bigger, badder, better model called Roberta. So here's the funny thing. It turns out that the original BERT, as amazing as it was, actually had a hidden weakness. Researchers figured out that it was seriously undertrained. It had the potential to learn so much more, but it just hadn't been given enough data or enough training time to reach its full power.
So Roberta, which stands for a robustly optimized BERT approach, didn't try to reinvent the wheel. It kept the same basic architecture, but just gave it a much better training regimen. We're talking way more data, training for a lot longer, and using bigger batches. And what's really interesting is they found that the next sentence prediction task wasn't as helpful as they first thought, so they dropped it and let the model focus all of its energy on just the masked language model task. And the result? A much, much more powerful model.
Now, BERT and Roberta were incredibly powerful, but they were also giants. I mean, these models were massive and they were really expensive to run. This created a whole new challenge. How do you take all that amazing power and shrink it down into something smaller, faster, and more efficient for everyday use?
This whole challenge gave birth to two really clever new models. First, you have Albert, which used a trick called parameter sharing to shrink the model's size. And then you have DistillBERT, which used a technique called knowledge distillation to make the models smaller and faster. And just to really appreciate what these new models did, you have to understand the problem they were solving. The basic BERT model has hundreds of millions of parameters. Trying to use a model that big is super slow and expensive, and it makes it totally impractical for a lot of things, like, say, running on your phone.
Albert, which stands for a light BERT, had this just brilliant idea. See, a normal BERT is made up of a stack of layers, and each layer has its own unique set of parameters. The creators of Albert basically asked, hey, what if we just designed one really good layer and then just reused that same layer over and over again? This idea, cross-layer parameter sharing, drastically cut down the total number of parameters, making the model so much lighter with only a tiny hit to its performance.
DistillBERT took a completely different path. It used a process called knowledge distillation, and the best way to think about it is with a teacher-student analogy. You start with your big, powerful teacher model, that's BERT. Then you create a much smaller student model. Now the student's job isn't to learn from scratch. Instead, it learns by trying to copy the teacher's answers. It's basically learning all the shortcuts and insights that the bigger model already figured out.
And what's just wild is how well this method actually works. The final DistillBERT model ends up being about 60% the size of the original BERT, which makes it way faster. But here's the kicker. It still holds on to 97% of its performance. That is an incredible trade-off. You get a huge boost in efficiency for a tiny drop in accuracy.
So, after this whole whirlwind of evolution, we're now left with an entire family of BERT models. And the key takeaway here is that there's no single best one. It's really all about choosing the right tool for the right job and finding that perfect balance between performance and efficiency.
And this table really sums it all up perfectly. The original BERT is your solid, all-around, general-purpose starting point. If you need the absolute best performance and you've got the computing power to back it up, Roberta is your go-to. If you're tight on memory, Albert's efficiency is a total lifesaver. And if your top priorities are speed and efficiency, especially for things like mobile devices, then DistillBERT is the clear winner.
The journey from the original BERT to all of its descendants shows this incredible story of progress in teaching machines our language. They have, for all intents and purposes, learned to read. But that leaves us with one last, really fascinating question to think about. What comes next? What's it going to take for these models to go beyond just the text on a page and start to truly understand the incredible complexity of our world?